Hi, everyone. So first of all, I'd like to say thank you to Jelko and the rest of the team at Core AI for inviting me to speak here today. This is the first time I'm actually giving a talk at a conference in Croatia, so yeah, really happy to be here. So my name is Ivana. I'm about to finish my PhD at the University of Edinburgh. I actually have my defense in 12 days, so fingers crossed it all goes well, so I can become that kind of useless doctor that can't help anyone in an emergency. And right after that, I'm starting as a research scientist at Google DeepMind. So in case any of you had any kind of questions on what it's like working for Google or working for DeepMind, the answer is I have no idea, and ask me again in a couple of months. I have to apologize a bit in advance because I know this is a conference on applications of machine learning in industry, but I'm a scientist, so this talk is going to have, so it's going to be a bit more technical and mathsy, and it's going to have a few less like cool slides and like fancy videos and things like that. But yeah, bear with me. So, okay, so I'm not sure how many of you here are familiar with knowledge graphs. But I'm sure most of you have come across an output of one, even though you may have not known that. So for example, say you've never heard of Google DeepMind and you type DeepMind into Google search. And this is the kind of classic output that you get. So on the left-hand side, you're going to get the kind of classic results where you get DeepMind's homepage, some frequently asked questions, and maybe some news stories where DeepMind recently appeared in. But what we're interested in and what I'm kind of talking about in this presentation is essentially what appears on the right. And this is what Google calls a knowledge panel, which is generated from a knowledge graph. So a knowledge graph is essentially a graph-like representation of knowledge, where we have subject entities, object entities, and relations between them. So in this case, when you type in DeepMind, this knowledge panel is going to give you object entities that are related to the subject entity DeepMind through various kinds of relations. So then you're going to get results such as that DeepMind was founded in 2010 in London, and this founded is going to be the relation, and the object entities are 2010 in London. And also other kinds of things, that DeepMind has 1,000 employees, or that its parent organizations are Google and Alphabet. So essentially, all this information is stored in this like big knowledge graph, which is called, like in this case, Google knowledge graph. And this is just one example of like a general knowledge graph. So Google's knowledge graph was introduced in 2012 with the idea of representing like actual things, so actual real-world objects and the relationships between them, so not just like strings of characters. And in October 2016, the knowledge graph already held 70 billion facts, and it answered roughly a third of 100 billion monthly Google searches. In 2020, this has already grown to 500 billion facts, and I'm sure this is even larger at this point. Apart from Google Search, it is also used to answer spoken queries in Google Assistant and Google Home. So just to give you an idea of what this Google's knowledge graph looks like, so essentially we have entities. In this case, there's Mona Lisa, Da Vinci, Italy, and Michelangelo, and various others as well. And then we have relations between them, which in this case are represented as these colored edges between them. So for example, this red edge might tell us that Da Vinci painted Mona Lisa, the green one that Da Vinci was born in Italy, and the blue one that Da Vinci and Michelangelo are both painters or both artists. Okay, so this is all great. We've got these knowledge graphs, and we can use them to answer questions. We can also use them for various other things. We can use them for information retrieval, for fact-checking. People use them in a biomedical domain, so they use them for some kind of drug repurposing. I recently talked to a startup in Berlin, which are building like smart buildings, and they're essentially representing these components in their buildings using a knowledge graph. And this is all great, but like knowledge graphs, the problem with knowledge graphs is that they're actually very, very incomplete. So they have been mostly created by humans or some combinations of human knowledge and natural language processing techniques. And it is almost impossible to cover like all possible facts in the world. So there's just like an infinite amount of knowledge. And even if we were able to do that, knowledge is constantly changing. So for example, someone who was a president of a particular country 5 years ago might not still be a president now. So we don't want to be kind of manually adding this kind of information and manually filling in knowledge graphs. But luckily, we've got machine learning to do that for us. So just to give you an idea of how incomplete these knowledge graphs are, the free-based knowledge graph, which is one of the earliest ones from which Google's knowledge graph was partially created, in freebase, essentially 71% of the people have no known place of birth, and like 99% have no known ethnicity. So you can see that this is actually a big problem, which is why we need to develop methods that are capable of automatically inferring missing facts, which is also known as link prediction or knowledge graph completion. Okay, so just to kind of formalize this sort of task a little bit, I've created a little example, like a tiny, tiny knowledge graph of the British royal family. And here we have entities, which are in this case London, England, Queen, and Prince Philip. Relations between them are things like capital of and born in. And the first kind of representation of this knowledge graph can simply be this collection of triples that I've shown you. So we have, like, for example, this first triple has subject entity London, object entity England, and the relation between them is capital of. So then when we have this collection of triples, this is like a first way to represent our knowledge graph. However, this is not very useful. We just have like this kind of, lots and lots of text, essentially. So this graph-like representation that you've already seen with Google's knowledge graph might be a more useful way to representing and to looking at this kind of data. So essentially, again, so we have entities, which are nodes in the graph, and relations are typed directed edges between them, and the directionality of the edge tells us whether a particular entity appears as a subject or as an object in a particular triple. There's many different types of relations, and they can be symmetric, such as this relation married to, because the Queen was married to Prince Philip, and Prince Philip was also married to the Queen. They can be asymmetric, such as London is the capital of England, but England is obviously not the capital of London. And they can have various other properties, such as hierarchy and transitivity. I just wanted to relate this a little bit to what Davor talked about earlier. Essentially, he mentioned word-to-vec, and actually, like these relations that occur in word-to-vec, where we have man is to king as woman is to queen, is actually a specific type of relation. So this is all very related to what I'm talking about today. Okay, so now so what we want to do with link prediction essentially is, so if we know that the Queen was born in London, and London is the capital of England, in this case, we want to be able to infer that the Queen is also an English citizen. Now, to do that with machine learning, we need to go somehow from this graph to some kind of mathematical representation of this graph. And this is done by representing this knowledge graph as a sparse binary adjacency tensor of knowledge graph triples. So if you don't know what tensors are, they're essentially just a generalization of vectors and matrices. So vectors are one-dimensional data structure, matrix two-dimensional, and tensor is everything three-dimensional and above. So essentially, like a normal graph, for example, I don't know, who is friends with whom on Facebook, would have an adjacency matrix where we would say, like, where we would see like who's connected to who. Here, because we have multiple relations, we essentially have a matrix per relation. So once you stack all those matrices on top of one another, you essentially end up with an adjacency tensor. And this tensor is going to have a 1 if two entities are related under a particular relation, and everything else is going to be unknown. So again, the task of link prediction is to work out which of those unknowns correspond to true facts and which are false. So how do we approach this? So essentially, we need representation learning. So we need to somehow be able to represent entities and relations. So what is typically done in the field of knowledge graph representation is to represent entities as vectors or embeddings in some d-dimensional space. And relations, on the other hand, are represented as transformations that are applied to these entity embeddings. So we can either apply them to the subject, to the object, or to both of them. It's essentially a design choice. So if we just had one single relation, we might not need this relation-specific transformation at all, so we might be fine by just having embeddings for entities. But because we have multiple relations, and one entity participates in many different relations, that's why we need this relation-specific transformation. So then, once we've applied the relation-specific transformation to the entity embeddings, we also need some kind of proximity measure, such as Euclidean distance or dot product, to measure how close, in some sense, these relation-transformed entity embeddings are. And if they're close, we say those two entities are related under that relation, and if they're not close, we say they're not. So again, just an example. So if we have the subject entity London, object entity England, here we apply the relation-specific transformation for the relation capital of, and then we get these relations transform subject and object, and in this case, they should be close because obviously London is the capital of England. So what brings together entity representation, relation representation, and this proximity measure to assign a score to each triple is what we call a score function. So the score function should assign a high score if two entities are related under a particular relation, and a low score otherwise. And then additionally, we apply a logistic sigmoid to this score to transform it to a probability of a particular fact being true. And then we optimize these representation parameters using gradient-based methods to improve the prediction accuracy. So across most models, there's been many, many models developed in this field, and what is kind of common to most of them is that almost all represent entities as vectors or embeddings. And what differentiates different models is the type of relation representation that they use, which is in most cases either additive, multiplicative, or both additive and multiplicative, and the proximity measure. So, as I already mentioned, it can be dot product or Euclidean distance. So, in this table, I've given for each type of relation representation an example score function and various different models. Don't worry too much about this. So today I'm only going to talk about these multiplicative models, which are essentially maybe like the simplest kind to understand, but there are also models that still hold the current state of the art in knowledge graph completion, so it's definitely important to understand them. So here we have like the score function for multiplicative models, which is essentially, so we have the subject and object entities, ES and EO. And we have a relation-specific transformation. In this case, that is a matrix multiplication. So essentially, which is like the name itself, multiplicative models, the name itself says. Then essentially to obtain the relation transformed subject entity, we multiply the subject entity embedding with the relation-specific matrix to get the relation transformed subject. And then the implicit proximity measure here is a dot product, because we do a dot product between this relation transformed subject and the object to obtain a score. So these 5 models that I've put on the right-hand side are essentially different multiplicative models which differ by like the constraints that they impose on the relation-specific matrix. So they all kind of follow this sort of shape of the score function that I've shown you here. They just impose different kinds of constraints on the relation-specific matrix. So I'm going to talk about the first 4 models in the next slide, and then I'm going to tell you a bit more about the Tucker model that we've developed. Okay, again, don't worry too much about the equations above. I'm showing everything in pictures underneath it. So these are the score functions of the first 4 models. So essentially, one of the first models that got introduced, first multiplicative models and one of the first knowledge graph completion models in general, is called RESCAL. And here, like the score function of RESCAL is essentially the score function that you've seen on the previous slides. So the matrix that RESCAL uses is a full rank matrix. And RESCAL works relatively well, but the problem with RESCAL is that it has a quadratic number of parameters per relation. So it tends to overfit to relations that don't have a lot of data per relation. To kind of fix that, the next attempt was called DisMult. And in DisMult, the matrix is constrained to be a diagonal matrix. So this essentially fixes this problem of overfitting, because now we have a linear number of parameters per relation. But it limits the type of transformation to a stretch, which then immediately means that this mult cannot model asymmetric relations. So if you remember from the first couple of slides, I had that example of London is the capital of England, and England is the capital of London. So this mult would give exactly the same score for both of those, which is obviously wrong. So then to fix that, the next model that got introduced is called complex. And complex uses complex numbers to represent entity embeddings or complex conjugates. But don't worry about complex numbers, because this can all actually be rewritten in the real domain. And I'm going to show you that a bit later. And then the last model is like simply, which has these sort of like different kinds of constraints, essentially like values on like various half diagonals. So everything else is set to 0, and only those parameters are the learnable parameters, the ones displayed in blue. So now, in order to introduce the Tucker model, I just want to kind of briefly note that all these models are essentially different ways of factorizing that big binary adjacency tensor that I mentioned in the first couple of slides. And I'm aware that most people here won't be familiar with tensor factorization. So to kind of get to tensor factorization, I just want to take a step back and look at matrix factorization, which I'm sure almost everyone is familiar with. This is like the kind of classic example everyone learns in like a machine learning course. It is also known under the name of collaborative filtering, and it's used for recommender systems. So essentially, we collect some kind of data on ratings. So users have bought items. They've rated them with some ratings between 1 and 5 stars, say. And then if we want to find out, so not every user has bought every item. So if we want to find out whether a user would like a particular item, so we could recommend it to them, then what we do is we decompose this matrix or factorize it into 2 matrices, one for users and one for items. So then the columns of the first matrix and the rows of the second matrix essentially represent some kind of features that are specific to users or to items. So then if we want to find out whether a user would like a particular item, we train our model, and then we multiply the corresponding row of the first matrix with the corresponding column of the second matrix, and we get our score. So now you can see here that we have essentially 2-dimensional data. We have users and items, and we decompose it into 2 matrices, one for users, one for items. So, but with knowledge graphs, we have 3-dimensional data. So we have subject entities, object entities, and relations. So essentially, we need tensor factorization instead of matrix factorization. So just another example, say we want to model the structure of international relations where countries take actions towards other countries, so they can buy things, they can sell things, they can, I don't know, sign various treaties or things like that. And we want to predict whether a country will take an action towards another country. So again, we train our model, and in this case, we do tensor factorization. So these are the 2 main types of tensor factorization, and they're called Tucker decomposition and CP decomposition. And what they differ by is this kind of tensor in the middle, this smaller core tensor. So CP decomposition essentially doesn't have it, so it only has these 3 matrices that contain the features or embeddings for countries and actions. Whereas the Tucker decomposition has additionally this core tensor, which tells us about some sort of interactions between different features. So it essentially captures some kind of shared information. Okay, so now that I've introduced tensor factorization, I want to move on to Tucker. So as you may have guessed, so Tucker is a multiplicative model that is based on the Tucker decomposition of that big binary tensor of knowledge graph triples. So essentially, that big tensor is decomposed into a much, much smaller core tensor, this W here on the slides, and 3 matrices for the subject entity embeddings, object entity embeddings, and relations. So then to get to this familiar form on the right, which is the familiar form that you've seen for multiplicative models, we essentially multiply this relation and entity agnostic core tensor with the relation-specific vector, this small WR. And then we get this kind of familiar form on the right-hand side. So you may wonder, why do we even want to do that? So why do we want to do this like full-blown Tucker decomposition? Why don't we immediately start with what we have on the right? Well, there's two main reasons. So the first one is multitask learning. So essentially, by having this core tensor, rather than learning distinct relation-specific matrices, like with Rescal or complex, you can essentially think of the core tensor as containing a shared pool of prototype relation matrices that then get linearly combined using the parameters in the relation-specific vector to get this matrix on the right. So by doing that, we essentially achieve multitask learning across various entities and relations. So in some cases where we don't have a lot of data per relation, the parameters for that relation might get learned better using like these kind of shared parameters in the core tensor. The other reason is scalability. So by doing the full Tucker decomposition, we essentially have a linear growth of number of parameters with like the number of relations, whereas in the case of Rescal, this growth is quadratic. Essentially, so this is Tucker. This is the model that for knowledge graph completion that achieved state-of-the-art results when we introduced it. So we presented it at one of the 3 top conferences in natural language processing in the world, EMNLP in Hong Kong at the end of 2019. And it's since been used a lot, like in research and also in industry. So for example, a couple of months ago, I gave a talk at the AstraZeneca's knowledge graph group, and they're essentially already kind of planning to integrate Tucker into their model for drug repurposing. Here I just want to show you how previous models can be seen as special cases of Tucker. So those 3 matrices for subject entities, objects, entities, and relations remain the same. So the only thing that we change is the core tensor. So whereas in Tucker, all of the parameters in the core tensor are learnable parameters, here you can think of like dismult, complex, and simply as some kind of constrained versions of Tucker, where those parameters of Tucker's of this core tensor, where these parameters are not learned, they're just fixed to these values that you see here. So dismult is essentially equivalent to a CP decomposition with these ones on the super diagonal. Complex has various ones and minus ones, and simply has various 1/2s on various half diagonals. So yeah, they fix these parameters whereas Tucker learns them, and because of that, it has some kind of added flexibility and like this like multitask learning aspect. Okay, so now we've defined this score function, and we can choose anyone we like, any of the ones that I've talked about, whether it's Tucker, whether it's complex, whether it's the Rescal. So how do we actually train this model? So we initialize all the parameters randomly at first, and then we select a batch of training data, and then we compute the score, and we apply a logistic sigmoid to the score to get a probability. And then we use just a standard Bernoulli negative log likelihood or binary cross entropy to train the model. The issue here is that this loss function requires positive and negative samples, so it requires the labels to be 0s and 1s. But knowledge graphs contain only true facts, because there's no point in like storing something that is false. So we only have the data that is labeled with 1s. And this is actually an example of positive and unlabeled learning, which is like also like an active research area. So how do we get negative samples? Well, we need to make some sort of assumptions, and we assume that a knowledge graph is only locally complete, which means that we include all observed triples as positive samples, and we also take the missing triples that complete the pairs that occur in the observed triples as negative samples. And then we kind of, for each positive sample, we sample a certain number of negative samples. You may notice that we cannot guarantee that our samples will truly be negative, so we might get some false positives. But we kind of, because like only a small subset of all potential facts of all potential entries in a knowledge graph is true, in most cases, these are actually going to be true negatives. Okay, so just to conclude, so knowledge graphs are large collections of facts, where facts are stored as these triples, and we represent them as a graph. The issue with them is they're incomplete, but luckily we've got link prediction or knowledge graph completion. I've talked to you about various sort of models. I've introduced also our Tucker model for link prediction, which achieves state-of-the-art results, and that is mainly due to multitask learning between relations. In case I managed to somehow get you interested in this kind of stuff, so the paper is online, it's on arXiv, this is the title, the code is also online, it's on my GitHub profile. And yeah, so just before I conclude, I just wanted to take this opportunity to say, if there's anyone here who's kind of interested in a career in research or interested in becoming a scientist, feel free to reach out, I don't know, chat to me afterwards, or send me an email or contact me on Twitter, whichever of those. I'd be happy to kind of share my experiences. It's not like an ideal career path like any others. There's like ups and downs, but it can be actually really interesting and rewarding, and it's kind of cool. I mean, you're literally paid to think of things that no one has ever thought of before. So yeah, how cool is that? Thank you.
Yeah, just a first comment, fantastic. It's really interesting. A few things, first thing first. So you're mentioning drug repurposing, and I'm aware that there was some work with Jure Leskovac actually doing the same thing, similar. So if you can just like shortly explain how those two approaches relates.
I'm actually not familiar with that Jure Leskovac's work. Is it using graph neural networks?
Of course.
Yeah, of course
what
it
else?
is. Yes.
What else could it be?
So I don't actually know how, like, I mean, so okay, so graph neural networks are really widely used for normal graphs, so not for knowledge graphs. And part of the reason why they haven't somehow taken off in the knowledge graph world, why we're kind of still using these simple models, is in the fact that we have multiple relations. So that essentially means you would need a graph neural network per relation, or you would need some kind of smart way of like reducing the number of parameters. So I don't know how exactly they're doing it, but I'd be interested in like having a look at that, because like so far in the knowledge graph, like standard knowledge graph field, like these kind of models still perform better than graph neural networks.
I don't know much about except that it exists. Although his work is in a way similar. I mean, the domain is similar because obviously thing. Another question is more curiosity then. So basically the structure that you're studying here, basically that's a Kripke structure, multi-relational Kripke structure, and there's a lot of historical work from computer science and mathematics and logics about using I don't know, knowledge representations, knowledge logics, hybrid model logics, different kind of things, and formalism that could actually capture all of the expression that are used here. And actually, I know there was a guy in Edinburgh some 20 years ago, actually doing that kind of work, actually standardizing all those different languages that you can use to talk about the knowledge graphs. So was there any attempt to use this? I think it was called hybrid model logic or something like that, to actually use this as the input language for all those kind of models. Because the way I see it in practice, I always have to learn the new syntax for each knowledge representation.
Well, actually, there's been lately a lot of work that kind of combines logic and like this standard like embedding-based approaches, where because essentially there's also like different sort of relationships between relations, because one relation might imply another relation or things like that. So this is where logic comes in. So I haven't talked about it today, but yeah, we've been a bit looking into that now, like recently, and yeah, there's actually a lot of work on that.
Željko told me not to ask any more questions. Thank you.
Can talk later.
Thanks. So I wanted to ask about the scalability of this. So training, I mean, if you add, let's say, a new node in a graph, you add new links, do you have to retrain everything? Do you have some methods to kind of,
yeah, so this is essentially like probably the biggest issue of these kind of approaches, that you would have to retrain it, or so far there isn't anything smart you can do. This is kind of like where graph neural networks excel at, because you can just add stuff and you don't need to retrain the whole model.
What is the status of public data sets that are available for this kind of research?
So all of these data, well, I haven't actually mentioned any results. I thought it was going to be boring. It's just a table of numbers. But yeah, all of the data sets that we work with are public, and they're actually extracts from this free-based knowledge graph that I mentioned, and WordNet, which is kind of relationships between words. There's also recently been published, I think it's called the Open Graph Benchmark or something like that, and they also have some knowledge graphs in there. So there's actually a lot of data to work with. Ah. Mm-hmm. Thank you.